except for the bottom row, we can use a heap or use an array to store this data structure. And that is nice because it gets rid of the overhead on a linked list. It's easier to use on memory. There's less memory involved. So that's why we would use a heap. Grab my eraser here. Now a heap, you can either have min heaps or max heaps. And basically the difference between those two are just going to be the root node. Or not really the root node, but the min heap means the smallest value is going to be in the root node. And a max means the highest or largest value is going to be in the root node. Okay, so let's start off by creating a heap, kind of from scratch. And then I can go over, so we'll go over insertion and then percolate and deletion. Okay, so let's say we'll start off with an easy one. I'll just throw some values in there, 5, 6, 3, 1, and 7. Okay, so we have our little array here. And we're just given this random array of values, and we want to turn this into a heap, and we'll have the array down here that is going to be the result when we're done turning this into a heap. So we have, it looks like 5, 1, 2, 3, 4, 5. Okay, so how we start with the insertion or creation of a heap is you're always going to add to the bottom left, okay? So when we start out, obviously, let's take this guy, 5. Obviously, we don't even have a structure yet, so it's just going to be the root node. Okay, and then let's go to number 6. So number 6, like I said, we're always going to go to the bottom left spot. So the bottom left would be here, okay? And this is a binary heap, so it's going to have 2 nodes, 2 children for every node. Okay, and then 3. So, and we have to do the check every time we insert a node. So 6, this is a min heap, by the way. So I'm just going to write that over here, min heap. So at the moment, 5 is less than 6, so we're okay. We don't have to do any swaps. Okay, so let's insert 3. So when we're on this level, we have to fill up the level first. So remember, every node has to have 2 children. So we need to fill up this guy, so we're going to add it here. So 3 will go there. Now we can see here. Now it doesn't matter about the children. We're not comparing those like in the binary search tree where we have to do rotations. In a heap, we're just going to make sure that the parent is, well, in a min heap, that the parent is less than the child. So in this case, we added 3. 3 is smaller than 5. So what we need to do is a swap. You might hear it as percolate, bubble up, and I'm going to reference it as a swap. So 3 and 5 are going to, 3 and 5. Okay. So that row is full, this row is full. So we got 3, now we're going on to 1. So this is full, so now we go to the bottom left. So over here, we're going to add 1. Check the parent node. The parent node is greater, so we need to do a swap. 1, 6. Check the parent node again after that swap, and we notice that 3 is larger than 1, so we need to swap again. Like I said, the smallest value is always going to be the root node. Okay, so if we check here, everything smaller is towards the top or a parent. Okay, and then our last one is 7. So 7 again, going to the left, this one is taken. We're going to the bottom row and insert left to right. So 7, and this node needs 2 children. So 7 is greater than 3, so we are good. We're okay. Now let's just add a couple more values to get the hang of this here. So I'm going to make up some random values. Let's just say 2 and what else do we want to do here? Let's add 4 to the heap. And then we'll add 2 more spots down here. Now this is just going to be what our heap looks like in the end after we finish this up. Okay, so we just added 7. 7 did not need to do any swap or bubble up or call the, when you're actually coding this, you might call it the percolate method. So we're okay. We don't need to do anything. Let's add 2. So again, we go to the bottom row, left to right. This node here already has 2 children, so we got to go to this guy. This will be a 2. Now 5 is greater than 2. This is a min heap, so we need to do a swap. 5, 2. And 2 and 1 are good. 1 is smaller than 2. Now let's add the 4. So bottom row, left to right. This guy still needs a child. So now we check to see if we need to do a swap or bubble up, and we're okay. The heap is full. Now the heap, like I said, to be a heap structure, it's always going to be full except for the last row here. Like we could take away this and it still meets the requirements as a heap. And the reason why is because we can put that in an array, and we know the index formula to, so let's say this is I. So in a binary heap, if we want to get to the right child of any index, we're going to take, it'll be 2i plus 1 will be the left child, and then 2 times I plus 2 will be the right child, right, left. So that's the nice thing about a binary heap. You can go to any index and times it by 2 plus 1, and you will find the left child, and then 2 times that index plus 2 will give you the right child. So this is kind of showing you how the heap works and what it's good for. Like I said, it is nice to be able to store this structure in an array, because an array takes up less memory, and you can access the children pretty easy by knowing the index of the parent. Okay, so let's clean this up a little bit here. Okay. All right, so now this is full. Now let's rewrite what the array is going to look like. This is what it's visually going to look like as far as what the heap looks like. But in an array, it is just going to be, this is the 0 index, this is the 1 index, 2, 3, 4. So pretty easy. Just kind of goes in order left to right. So I'm going to write the indexes here. 3, 4, 5, 6. So we actually have 7 values in here, and like I said, left to right, 1, 3, 2. Now you notice, I mean, this isn't going to be in order because the children node it doesn't matter. That's the difference between the other data structures and trees that you will go over, is it doesn't matter. You don't need to do any rotation or anything like that. As long as the parent node is smaller than both these guys, we're good to go. So 1, 3, 2, speed up here a little bit, 6, 7, 5, 4. Okay, so that will be the aftermath. This will be a heap, a min heap, and it's using an array data structure, which is great for memory compared to a linked list or a tree type structure. Okay, so now I'm going to go over deletion really quick. Just a high level, there's a couple different things. Let's get rid of these little guys here, these indexes. Okay, just clean it up a little bit. So whenever you're deleting a value from a heap, the key thing to know is we always want to delete the last guy in the array. So I probably shouldn't erase this array, but 4 would have been the last guy in the array. Because we know how to delete that. That is easy. That doesn't goof up our tree, okay? Or our heap, I'm sorry. So we always want to try, or we always will be deleting this last node when we want to remove something from our heap, okay? So let's say we wanted to delete 4. Obviously, that's an easy one. We just delete it. If we have the array down here, same thing. We could just remove that value. Now, the tricky part becomes when you want to delete, let's say 1. We'll just go to maybe the hardest example. So if we delete 1, what are we going to do from here? Because our heap is all screwed up. The same thing for the array. We would have a missing piece right here. It's not full except for the last row, which is one of the requirements. And there's a couple ways we could try to, resort this heap, but it would just be a pain. So what we're going to do is you're always going to take the node that you're trying to remove, or the value, and you're going to swap it with the one that we know how to delete, because we can just take it off. So this was 1 and this was 4. Let's swap the 4 up here, and let's throw the 1 down here. Now, as you can see, we can delete the 1. That is easy. That doesn't goof up our tree. I keep saying tree, I'm sorry, heap, and then it does not goof up our array. Now, this is a 2. Now, obviously, the 4 is goofing up our heap right now. This is not correct. So what we're going to do is kind of swap, or like we were doing before when we were adding a child and it needed to go up, we would bubble it up by swapping. Same concept here, except we're going to bubble it down by swapping. So we're going to find the smallest of the 2 children to swap. Because if we swapped it with 3, the root node wouldn't be the smallest, because this is a 2. I'm going to clean this up a little bit. That look a little nicer. Okay, so like I said, if we swap this with 3, then 3 would be at the root, and that would not be the smallest number, because 2 would still be here. So you always want to, when you're coding this, you want to check both the children and find the smaller value and swap. So 2 would be the smaller value. That's going to go to the top. 4 is going to go down here. Now this is kind of a small heap, so that's it, because 5 is larger than 4. The heap looks good. The only incomplete row is this bottom guy here, which meets the requirement for a heap. We're all set. Okay, so I think that's it for heaps. So just a high-level overview, going over the basics of the min heap. Max heap is just going to be the same thing, except for you're going to have the max values at the top. That's it, guys. So thanks for watching. If you have any questions, comment below. Hit that like button. Thanks, guys. Thanks for watching.